All right, in the previous videos, we were talking all about Lewis dot structures and how we can symbolize how the electrons are all shared in order to make our different structures. Well, sometimes there's more than one way to build a valid structure, and those types are called resonance structures. Resonance structures are going to be when you have two or more equally valid electron dot structures. And we're going to specifically look at ozone and sulfur trioxide for these. Okay, so ozone, it has this formula O3, and sulfur trioxide has SO3. And the way that scientists were able to prove this is by looking at the length of the bonds between the atoms. Um, what we're basically doing in these resonance structures is we are moving lone pairs and double bonds. So you'll see that there is no clear one way to draw these, and there's not one clear example where the single or double bond is located. So let's just say, for example, the bond length of a single bond is going to be 2 centimeters. It's not centimeters, but really, really far. Let's say nanometers, okay? And the length of a double bond is going to be 1 nanometer because double and triple bonds are going to be closer together because there's more interactions between them. Okay, a resonance structure is going to have something that resembles a 1.5 bond with a length of exactly 1.5, okay? 1.5 nanometers. Oops. And you'll see exactly what I mean in the next slide when we start drawing these out. Okay, so let's take a look at ozone. Ozone is a gas that exists in our atmosphere. Ozone has the formula O3. It blocks out harmful UVA, UVB rays. Oxygen has 6 valence electrons. It needs 8 in order to be happy. So oxygen, um, we've been drawing like this, or for these examples, I like to show it with the individual electrons like so. All right, so if we take oxygen and we fill in 6 valence electrons for each one, we can make this bond so that it will show 8 for each one. So what we do with these guys right here is we have one lone pair, another lone pair, and then I'm going to double bond to these two, making this one a lone pair and a single bond right here. So what about this oxygen right here? It has a lone pair, and a 7th electron right here. So what happens is this electron notices that he needs a friend, so we end up getting 3 lone pairs on this first one. This oxygen has 1 lone pair, and then we have 2 lone pairs on this one. Okay, so what scientists typically do is they label their oxygens 1, 2, 3, showing that the oxygens don't move and it's the electrons that move. This is one valid structure, okay? The other valid structure is going to do the same thing, but form the double bond on the other side between oxygens 1 and 2 instead of between 2 and 3. So if we take a look at this one, we have our oxygen, oxygen, oxygen. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 5, 6. And then we start bonding. And when we bond, now we have our lone pair, double bond, lone pair, bond, lone pair, and this electron sees that he needs a buddy, so our electron goes over here to show the double bond between oxygens 1 and 2, and a single bond between oxygens 2 and 3. And I'll label these in here again. Okay, so there is more than one possible way to draw these. Okay, this double-headed arrow means resonance, and it means that these are equal and they are valid and both work. And what I was talking about on the previous slide is say that this bond length is 2 nanometers and this one is 1 nanometer. So then this one would be 1 nanometer and this one would be 2 nanometers. Well, if they take a screenshot of the whole thing, they find that the actual distance is 1.5 nanometers, somewhere in between. So this resonance keeps flapping back and forth between these two over and over again. So there's not one single moment in time when it's always between one or the other. So half the time it's this, half the time it's the other. So it kind of melds into this 1.5 nanometers in bond length. Okay? Same thing is true for our SO3 resonance structures. But our central atom, which is sulfur, has 3 oxygens around it. Oxygen 1, oxygen 2, oxygen 3. Oxygen 1, oxygen 2, oxygen 3. Oxygen 1, oxygen 2, oxygen 3. So what you'll notice is some of the time the double bond exists between sulfur and the first oxygen, sometimes between the second oxygen and sulfur, and sometimes between the third oxygen and sulfur, resulting in 3 equal resonance structures. Okay, these electrons here are going to force these different electrons to move and swap and bump back and forth between them. And the proof in this is when they do take measurements, the bond length is about a 1.33 nanometers in length. Now, again, I'm not sure if that's the exact length, but relatively speaking, it exists somewhere between having a third of the time the double bond here, here, and here, etc., etc. with those. So that is an example of how we can have multiple possible structures for the exact same molecule, otherwise known as resonance.